Hi, my name is Adam, also known as the Bearded Engineer, and today we're going to be talking about the combination sum problem. So an overview of how we're going to go about this is first we're going to read the problem statement, and we're also going to gather requirements to the problem. So essentially boil the problem down into a list of inputs, outputs, constraints, and then what we're going to do is we're going to go through an example to make sure that we understand what the problem is asking. Next, what we're going to do is we've already seen an example, and now we can build that out to a generalized approach to how to solve the problem. And then 4, we're going to review the Python code that implements this approach. So the first thing is let's read the statement here. Okay, so let's see. Given a set of candidate numbers, candidates, without duplicates, so already I can see that there's an input candidates, I'm going to call it canned, which is an integer array. And there's already a constraint that we see on the problem without duplicates. So no duplicates here. Okay. And we're also given a target number. So target, and that's an integer as well. Find all unique combinations in candidates where the candidate numbers sums up to target. So what we're going to do here is, what is the output? It's going to be all, I'm going to get back to this, unique, all unique combinations. And the constraint is such that sum equals target. Okay, perfect. And then there's an additional constraint here in the problem that the same repeated number may be chosen from candidates unlimited number of times. So we can choose same number here. Okay, let's just see, all numbers will be positive, okay. So while this is no duplicates, so it's positive only, and the solution set must not contain duplicates. Okay, so that's good. So we've understood the problem here, and so now it's always good to write this out here, so then effectively we don't have to actually look at the problem again, because we have all of the list of requirements over here. So that's number 1, read statement and gather requirements. So 2, let's go through an example here. So let's give the example of 2, 3, 6, and 7. So what we want to do is we want to find all combinations, and combinations are, it's an array of numbers where these numbers come from the candidates array. So for example, I can have 2. I can also have 2, 3. And you see here, we actually are able to use the same number multiple times. So 2, 2, 3 as well. And let's try 2, 3, 2. And so we see here that this is actually not valid because it says find all unique combinations. And a combination, this has 2 2s and 1 3, while this has 2 2s and 1 3. So this actually isn't a valid combination that we can consider. And then we also have, let's say, 7, which is another combination. Okay, so now what we want to do here is we want to append or commit the results, or commit all combinations where the sum is equal to 7. So we are going to have the sum be 7 here. Okay, so we see that the sum of this is 2. Of the next example is 3, 4, 5. This is 7, and that is 7. So you see here that the sum is 2, and it's not equal to 7. So the combination of 2 does not go into our output. Neither does this one. But you see over here we actually have a valid combination whose sum is equal to 7. So we are going to commit this to the output. And you can see here, this is actually another valid combination. So we are going to commit this. And it turns out that in this problem, these are all of the possibilities, but our program is going to have to programmatically search through all combinations and get all of the valid combinations. So what we have just done is we have gone through an example and we understand kind of what's going on. So what we're going to do here is we are going to put this out of the way. It's also good to save or keep in mind an example problem so that as we go through the problem, if we ever get stuck in the code, we can refer back to an example to help us. So the next thing we want to do is we want to look at the approach. So how are we going to do this? So in the problem statement, we actually see it saying, find all unique combinations. So what does that mean? It says all. And whenever you see something like all, or find all, or generate all, you're essentially doing some sort of exhaustive search through all possible combinations. You want to do it in such a way that you don't brute force every single combination. And actually in this problem, there are infinite combinations because there is the constraint, or we can go to our constraints, that we are allowed to choose the same number. Okay, so whenever we see all, we want to think of a DFS search through our combination space, and this is actually also backtracking. Okay, so let's see how we can start to think about the problem. Typically in a lot of these problems where you're trying to find a solution which satisfies some constraint, what we actually want to do is we want to start with the most trivial example, which is the empty set, or an empty combination. So in this case, the sum of this is 0. Actually, another way to do it, and this is actually how we're going to go about it in the code that we'll see later, is that we want to track the sum here as 7. So we initially initialize it to the target that is given in the problem. And what we want to do is we want to find a sum such that this 7 is reduced to 0. So let's go through this. Okay. Okay, perfect. So at this stage, we want to explore the different possibilities that we have available to us. And in this case, it is an n-ary tree or decision matrix, or a decision tree. And so what are these branches refer to? These refer to nothing more than the elements in candidates. Okay, so for each candidate, we have 2, we have 3, we have 6, and we have 7. So these are all of the possibilities, and what we want to do is we want to incrementally build up a partial solution. So in this case, it'll be 2. And then what we want to do is we actually want to check what the resulting sum is. In this case, it's 5 here. So we started with 7 and we've subtracted 2. So we have 5 more units that we want to add to this subarray or this combination in order to make it a valid combination. And so let's actually just explore this a little further. Let's actually visualize this in a kind of, let's start by going over here. So in this case, we would be selecting a 3. And so what that'll do is it will make the sum 7 minus 3 equals 4. So in order to form a valid combination, we already have 3 and we're searching for 4 more. Okay, so now what do we want to do? So let's actually consider further solutions. So we've already seen here that this combination of the element 2 does not meet the constraint of adding to the target. So what we do is we can make another choice. So in the problem statement here, remember the constraint is we can choose the same number. So we can actually make the same exact choice as the one before. We can choose a 2 again, a 3, a 6, or a 7. So if I choose a 2 here, I will get the array, the combination of 2 and 2. So again, that is going to be 5 minus 2. So I'm looking for 3 more over here. Okay, so actually if we then traverse this once further, we'll actually see something interesting. Here, we are going to get a combination of 2, 2, and 3. And because we had three more that we needed to search for, and we've used 3 up here, we get 0. And this 0 represents I need to search for 0 more in order to make this a valid combination that should be appended to the solution. So actually, this is part of the solution. And so if we see 0, this is going to be our base case, our terminating condition, where essentially what we've been doing up until this point is we've been recursing further down the tree. And we recurse until we hit a base case. And in this case, the base case being 0 is going to be our terminating condition. Okay. So now this is how we search for, so we do this recursively throughout all the elements, and we get to these leaf nodes. And so something else to consider, or something else that's interesting, is let's view this node right here. Actually, let's view this node right here. So we do the same thing. So we have 2, and we're selecting 7 to be in our array, in our combination. So this, we are searching for 5, and we see here 7. So this actually becomes minus 2. So what this means is that I've over-selected a quantity. I have too much of the quantity. So in this case, this is also another terminating condition where we don't want to explore any further either. So it looks like there's 2 terminating conditions, which are that stop the recursion down the tree. And so the terminating conditions are it's essentially this left to go is greater than or equal to 0. So in that case, we terminate. And these are actually base cases. So maybe I will say base case. So the base case is left to go is greater than or equal to 0. And so what's the difference between this guy and this guy? Well, in this guy, this is actually a valid solution. So what we can do is we can say if left to go is equal to 0, then we want to append solution. So these are our 2 base cases, and that's what we have demonstrated here and here. Okay, so let's go through the problem to see if this approach is the entire approach that we need to take. So it says here that we need to find all unique combinations. So let me actually just illustrate that via one more node here. So again, remember what we've been doing is up until this point, we've exploring 2, 3, 6, and 7. So at every level, we explore all candidates right over here. So in our code, we're going to express that as a for loop. And so let's draw what's happening in here. So in here, we're going to have a 3, and we're going to be appending a 2. Well, you see over here, there's actually a 2 and a 3 solution over here. These two nodes are the same. Why is that? Because 4 minus 2 is going to be 2, and 5 minus 3 is going to be 2. So the sums are the same, but really what matters is that there are the same element, 2 and 3 and 2 in this array. And for combinations, the order of the elements don't matter. So these are actually the same. So if we want our program to not explore one of these nodes. And so how do we do that? So that comes to another, that gets to another point, which I'm going to explain right now. So if you look here, what are we doing at every single node? We are choosing an element to add to our partial solution. So in this case, we choose 2. In this case, we choose 3. But to go one step further, when we're choosing 2, we actually have the option of choosing 2 or 3 or 6 or 7 again. And so recursively, this entire subtree, as you see here, that starts with a 2, contains at least 1 2 and contain up to more 2s up until infinite number of 2s, because we allow for unlimited of the same digit. However, once we get to 3, what happens? So when we've gotten to 3, remember this subtree includes 1 or more 2s. Therefore, this subtree should include no 2s, because if it included a 2, then it would be found in this subtree. So what we want to do is we actually want to cut off this branch. Okay? And so now let's actually elucidate this once more with the branch of 6. So in this case, we have 6, and we have 4 decisions again that we can make, 2, 3, 6, and 7. However, we can apply that same logic to this subtree. If I've chosen a 6 from an empty set, if I've chosen a 6, that means that I have already considered all of the 2s that I've wanted to explore. And I've also considered all of the 3s I've wanted to explore. So you see here, at every level, as you iterate across the candidates, what you want to do is you want to not explore elements prior to this value here. And how do we do that? And then so let's just, for complete clarity, let's have the 7 coming off of here. I don't have that much more room. What we want to do is we don't want to explore the 2 any further. We don't want to explore this 3 any further, or the 6. So you see here at every level as you go across, we are trimming off 1 branch, 2 branches, 3 branches, up until the case where you're only left with 1. So how do we actually implement this? So we know that the branches that we start at, the branch that we start at, right here, is the same index as the branch we've started at here. So you see this right here is the 0, 1, second element in candidates. And here we are starting at 0, 1, in the second element. So what we're going to do is from level to level, we're going to pass the index down, the index of my number down. And from there, we are going to, in the child, we are going to recurse starting at that index and going forth. And so this right here represents what I believe is the entire solution that we have to keep in mind, or is the entire approach to the problem. So what I'm going to do is over here is, and let's see if I have room. Okay. What I'm going to do is I am going to bring in the code. Okay, so as we see here, this is the code. And so we want to ensure that this code somehow is implementing the approach that we are talking about. Okay, so what we do is here's our main function, combination sum. And so what we're doing is we are initializing an array called result. We are passing that into our actual DFS solution. And then at the end, we're returning result. So therefore, what the job of helper is to do is to append any valid solution to this result. Okay, so now that we see that, what are our other inputs? So remember, we are passing in, of course, at every level, we need to iterate over the candidates. So I've called it nums here because it's shorter. And remember what we said is we want to start at target. So we want to start at a value of 7, a target of 7. And then what we want to do is over time, we are going to want to check if target is 0. If target is 0, excuse me, then we will want to append this result. Okay, so this 0 right here represents the index. And remember, the index is going to be used to cut off the branches that we don't want in order to ensure unique combinations. Okay, so now so this partial solution represents what's inside of this node, what's inside of every single node. And this result is passed out throughout the tree such that if you have a valid combination, then you append the result. Append the partial solution to the result. Okay, so now that we've understood the inputs to our DFS problem, let's actually go through the code in a little more detail. So the first thing we do is, please give me like 3 more minutes. What we want to do is, so at the beginning, we want to check our base cases, our terminating conditions as we see here. So the terminating condition is if target is equal to 0. So in that case, as we've explained, we just want to copy that partial solution, whatever's inside of this node, to the result. Okay, so then the next thing we want to do is if we get to this for loop, what we do is the condition is that target has something more to it. So we want to traverse the tree further. So what we want to do is we want to iterate over our candidates, over all of our numbers. And so remember I said that there's actually 2 base cases. Well, you can actually add the second base case inside of the for loop. So what does that mean? Down here, where is it? Down here, we've started at 2. So we have our partial solution being 2, which means we have 5 left. And so what the explanation was is if you try to add a 7, then you're going to get a negative target. So what you can do is actually within the context of this node here, as I'm exploring my children, what I can actually do is if the number, so if num is greater than the target, then what does that mean? That means that if I would recurse into that next solution, I'm going to get a negative value. So instead of adding over here, if target is less than 0, then return, you can actually, this is called a branch, a bounding function. So this is called the bounding function. And what a bounding function is given all of your possible combination, or all of your possible branches that you can explore, you are bounding some of them. You are pruning some of them, and you're doing this in a proactive approach. Instead of waiting for the node to say, oh, I'm actually not correct, I'm actually not a valid solution, you can actually bound it up here, and that's what I'm doing. Okay, so then what we're going to do is we have to encode. So up until this point, if we get over here in the code, we want to use this candidate as and explore the possibilities. So this is where the backtracking comes in. So in backtracking, what we do, and you see this over and over again in backtracking problems, is it's a three-step approach. What you do is you choose the number to be a part of your partial solution. Okay, so you choose. Then given that choice, you explore. And then what you do here is you unchoose. So you choose, explore, and unchoose. You add 2 to your partial solution. So given the empty set, what you do is you choose a 2, so now you have a 2 inside of your partial solution. And then once you come back here, you actually want to remove the 2 such that when you choose the 3 next, this solution right here is not going to be polluted with a previous choice on the same level. So that's very important. And now let's actually just let's explore the helper function. And then once we've explored the helper function, or the recursive step, then we have effectively solved the problem. So what we do is we pass in the same nums array. And what we do here is we want to decrement the number from our current sum. So if we've started at 7 and we're choosing the number 2, we have 5 left. And so that's why you see target minus num here. Okay, so this I right here is remember we explained in this approach that what you want to do is you want to start at the index of the current choice. So you see here, our num, let's say, is 6, and this corresponds to an index of 2. So what we want to do is we want to pass this in as 2. So instead of starting at 0, which is exploring every single possibility, we are starting at 6, and we are only exploring those 2. So that's why we pass in the index. And then all we do is we pass in the partial solution and the result. And so this right here is the code that implements our full approach, and this approach embodies all of the different bits and pieces of the algorithm that we have to be considerate of. So in conclusion, what we've done is we've read the statement and we have gathered our requirements. And so now we actually don't really need to look at this problem statement anymore because we've encoded everything that we need in our requirement gathering phase. The second thing we've done is we have written out in an example and gone through the example kind of by hand and just saw like how things should work. Once we got a good sense of the example, a good grasp of the example, we started to look into the approach. And so for that we pulled from our backpack the backtracking and DFS method or approach. And what we did is we went through this example in more detail, and we outlined every single bit of the problem that we need to consider. And then what we did is we've reviewed the code and saw that how every single line in the code serves to do something else in this, serves to implement one bit in this approach here. So I hope this helps, and don't forget to subscribe and like the video. Thank you so much.